Hi, everyone, and welcome to this week's videos for topological data analysis in neuroscience. So in this week, we'll be talking about some of the theoretical foundations of persistent homology. Right, so persistent homology has a very nice theoretical foundation to it. Right, there's the algebraic decomposition theorem, which shows that we can use persistence diagrams to actually break down persistence modules into nice sort of building blocks. We can define a distance on persistence modules, and this distance is given by a notion called interleavings, which we'll go over. And then there's a corresponding distance between persistence diagrams called the bottleneck distance. And finally, we have the bottleneck stability theorem, which says that persistent homology is stable. So this is crucial for applications and a very important and nice result that we'll see. Okay, but the first thing we're going to go over in this week's videos is the algebraic decomposition theorem. So we're going to start with persistence modules, right? So what is a persistence module? Well, we've seen RIPS complexes before, right? RIPS filtrations, right? And really what these are just, they're sequences of simplicial complexes, right? We have a simplicial complex at for each t in the reals. And when t is less than or equal to t prime, we get an inclusion of the RIPS complex at t into the RIPS complex at t prime. Yeah, so now it's not important that we use RIPS complexes here. We can use any method of getting a filtration at all. Okay, so now if we apply homology to this filtration, what we're going to get, right? So homology takes a simplicial complex and gives us a vector space, right? So when we apply homology to this filtration, what we're going to get is a sequence of vector spaces, right? Before we had a simplicial complex for each t in the reals. Now we're going to get a vector space for each t in the reals. But we had more than just a sequence of simplicial complexes, right? We had that the simplicial complex at time t, or scale parameter t, included into the simplicial complex at scale parameter t prime, whenever t was less than or equal to t prime. So this inclusion, these inclusions are actually simplicial maps, right? And homology doesn't just associate a vector space to each simplicial complex, it also associates a linear map to each simplicial map, right? And so all those inclusions are simplicial maps. So those inclusions are going to induce linear maps, right? So we start out with a sequence of simplicial complexes and inclusions between them. Applying homology is going to give us a sequence of vector spaces and linear maps between them, right? So we're going to have a linear map from the homology of the filtration at scale parameter t to the homology of the filtration at scale parameter t prime whenever t is less than or equal to t prime. One thing I want to point out here is that, and this is a common misconception with homology, we started out, these maps were actually inclusions, right? The simplicial maps are inclusions here. We're including the RIPS complex at scale parameter t includes into the RIPS complex at scale parameter t prime. That does not necessarily mean that the homology at scale parameter t includes into the homology at parameter t prime. That's not necessarily the case, a common misconception. So these linear maps are not going to necessarily be inclusions, but that's okay. We still have linear maps. Okay, and so we call the collection of all of these vector spaces together with all of these linear maps a persistence module. But yeah, so on the last slide, we started with a filtration and got a persistence module, but we can actually shortcut that process, really. So we don't need to start with the filtration at all. We can just define a persistence module sort of in a vacuum. Right, and so a persistence module, we're going to use, for us, persistence modules are usually going to be indexed by the reals. So this just means we're going to have a vector space for each t in the reals. And we're going to have linear maps, right? So a linear map from the vector space at t to the vector space at t prime, whenever t is less than or equal to t prime. So this is basically the same thing we saw on the last slide, only we're not starting with a filtration right now. We're just defining this in general. Okay, so we've got these persistence modules now, and you can kind of think about these persistence modules as like a generalization of vector spaces. And just like with vector spaces, there's a whole lot of things we can do with vector spaces. One of the first things we typically do with vector spaces, though, is ask, what does it mean for two vector spaces to be the same, right? What does that mean? And of course, the concept with vector spaces is that of a linear isomorphism, right? Two vector spaces are the same if you have two linear maps, right? So V and W are the same if we have linear maps, one from V to W and the other from W to V, such that they are inverses of each other. The compositions give us the identities. There's going to be a similar condition for persistence modules, right? So an isomorphism between two persistence modules. And really, you should think about this as meaning two persistence modules are essentially the same, right? So VT and WT are going to be essentially the same, right? But really, formally, it means it's an isomorphism is the condition. So what do we need for this to, for them to be essentially the same is, well, we need linear isomorphisms. So we have here, we need a linear isomorphism between, right? So VT, we have a vector space for each t in the reals. Same with WT, we have a vector space at each t in the reals. And so for them to be linear isomorphic, well, first of all, we need VT to be isomorphic to WT for each t in the reals. This is just the usual isomorphism of vector spaces. But we also want these isomorphisms to be a bit nicer than that. We want them to have some more structure, right? Because our persistence modules have more structure. Just the first condition that we have linear isomorphisms would be a perfectly good condition if all we had was a sequence of vector spaces, but we have more than just a sequence of vector spaces. We also have maps between them. And so we want this isomorphism of persistent modules. We want it to not just say that the vector spaces are the same, but also we want it to sort of tell us that the maps between the vector spaces are in some sense the same. And so for that, we're going to use this condition here. And so it's perhaps best seen in this diagram here. So basically, let's say we have t less than or equal to t prime. And so now there are sort of two ways we can go around this square, right? First, we can go zeta t to zeta t t prime, right? So this is just the map from vt to vt prime. Right? T is less than or equal to t prime. So we have this linear map here. But now we want, well, so we're going to have a linear isomorphism from vt prime to wt prime. And so that gives us this, this map here from vt prime to wt prime. But what we could have done instead is we could have first gone from vt to wt, with the map LT, and then we could have gone via eta t prime from WT to WT prime. So we can take the top path around the square, or we can take the bottom path around the square. And what the second condition is saying is that the composition of these two paths should be equal. It should be the same. It shouldn't matter which path we take. And you can kind of think about this condition as telling us that the maps between not only are each of the vector spaces isomorphic, but the maps between them are in some sense the same. Okay, and so yeah, this is what it means for two persistence modules to be isomorphic. And we'll see later on that we can actually replace the reals with any partially ordered set. And this leads us to a notion that's called multi-parameter persistent homology. This is a very active area of research right now, and it's a topic we'll see later on in this course. Okay, so just like with vector spaces, right? The first thing we answered here was, what does it mean for two persistence modules to be isomorphic? And that was sort of analogous to the setting of vector spaces. Now let's look at certain other structural elements. Right, so with vector space, there's all sorts of different things we can do with them. Perhaps the simplest thing we can do is just add two vector spaces together, right? Take their direct sum. And we can do the same with persistence modules. So if we have two persistence modules, VT and WT, we can take their direct sum, and this is just going to be, right, we're just going to take the direct sum coordinate-wise, right? So with VT, we have a vector space for each t in the reals, and same thing with WT. We have a vector space for each t in the reals. So what we can do is we can just add those together coordinate-wise, right? So to add a V and W here, what we're going to do is it's just going to be the persistence module that at parameter t is just going to be the direct sum of VT and WT. Right, that's still a vector space. And then, well, what are the linear maps? Well, the linear maps are we're just going to use the linear maps coordinate-wise, right? So if we want to get a map from VT plus WT into VT prime plus WT prime, well, what we can do is we can just define the map on the first coordinate, which is VT. And we have that, right? We have a map from VT to VT prime. And we also have a map from WT to WT prime. So we can just define this map coordinate-wise, right? We can just, this map is just going to take the first coordinate to, it's just going to use zeta to give us the map from the first coordinate to the first coordinate here. And then it's going to use eta to give us the map from the second coordinate to the second coordinate. And so this is how we take direct sums of persistence modules. And so this is important because it gives us a way of building up persistence modules from smaller persistence modules. And this was very important in linear algebra with vector spaces, right? We can build up any finite dimensional vector space from like a sort of very basic building block. And so that's actually going to be the case here. And so this leads us to the notion of the algebraic decomposition theorem, which says that we can always build up any persistence module as just a direct sum of certain nice building blocks. Okay, so first let's talk about what these building blocks actually are. So these building blocks are going to be called interval persistence modules. These are sort of like the most basic persistence modules you can define. And so what they look like this on the right here. So here I've drawn two of these persistence modules. So they're always going to be 0 up until a certain point. At that point, they become, so let's say we're using Z mod 2Z coefficients here. So our field is Z mod 2Z. So our persistence module is just going to be 0, 0, 0, 0 up until a certain point, when it becomes Z mod 2Z. And it stays Z mod 2Z up until a certain point, and then it's 0 again. Or what we could also do is it could be 0, 0, 0 up until a certain point when it becomes Z mod 2Z, and then it just stays Z mod 2Z forever. And then, right, it's not sufficient to just define the vector spaces at each point. We also need the maps between the vector spaces. And so what we're just going to say is that basically all of the maps from Z mod 2Z to Z mod 2Z, oops. All of the maps from Z mod 2Z to Z mod 2Z are going to be identity maps. So yeah, all the maps in between are either the zero map if either the domain or codomain is zero. Otherwise, they're just identity morphisms. So just like with vector spaces, how we could break down any vector space into just a direct sum of the ground field, right? Like if you have, say, R to the n, or any, let's say you have any, let's say you have an n-dimensional vector space over a fixed field K. Well, we know that that field, or sorry, that vector space is just going to be isomorphic to K to the n. So in linear algebra, K is sort of the basic building block, your ground field. Here our ground field is Z mod 2Z. And you can kind of think about these interval persistence modules as playing the role of the ground field in persistence. Okay, so now we're ready to state the algebraic decomposition theorem. So if we have a tame persistence module, then the persistence module is isomorphic to a direct sum of these interval modules here. So there's just going to be possibly a bunch of these different intervals, but we can always break down a persistence module into just a direct sum of these interval modules here. All right, and so this is a very nice structure theorem. It tells us that there's this very nice structure with persistence. And we can visualize this with barcodes. Right, so what we're looking at here, essentially, the algebraic decomposition theorem tells us that every persistence module breaks down into a direct sum of these interval modules. So if we just look at this, really it's going to be a multi-set of intervals because we could possibly have some intervals be repeated. But if we look at this multi-set of intervals, right, that's going to uniquely define our persistence module, right? If we know that multi-set of intervals, we can reconstruct our persistence module. And that's what's called a barcode in persistence. So that's what we're looking at here. We're just looking at this multi-set of intervals. So each of these bars here represents a homology feature that was born a homology feature that was born wherever the left endpoint of the interval is and dies at the right endpoint. So we can see with zero-dimensional homology, everything was born at 0 and dies somewhere except for one feature, right? And this is because right, zero-dimensional homology is just counting connected components. Of course, every connected component begins at 0. Right, because we're working with with RIPS filtrations and stuff where we start with just all our vertices. So we're starting with all our vertices. So therefore we're starting with all of the connected components, and then we're just sort of linking them up, which corresponds to killing connected components. All the way out until eventually we have just one connected component. And that's why we see this one bar that is born at 0 and just goes on forever and ever and ever. It never dies. And that's because eventually we have just one connected component, and that one connected component never dies, right? We don't ever go from one connected component to 0. So that's why we have that one bar that lives on forever. And so here, this barcode is broken down by homology. So we have not just H0, zero-dimensional homology, but also H1 and H2. And so H1, this is representing holes in our space, while H2 is representing sort of cavities, like sort of three-dimensional, three-dimensional holes, sort of. Yeah, so this is barcode. So these give us a way of visualizing our persistence module. right? And so just more formally, right, whenever we can always pick a decomposition, the algebraic decomposition theorem tells us that we can decompose any persistence module as a direct sum of interval modules. And we call this decomposition the barcode here. And yeah, so the barcode it always encodes where homology is born and dies. So an interval from A to B appearing in the barcode means that a homological feature was born at A and died at B. And so barcodes are actually equivalent to persistence diagrams. So if we have, so let's look at this persistence diagram on the right. So we can interpret this persistence diagram as meaning that there were two features that were born at 2 and died at 4, right? If we look at this blue circle, the 2 there means that, right, there were 2 features that were born at 2 and died at 4. And then we have a 1 at 1 and 5, which tells us that 1 feature was born at 1 and died at 5. We can actually view this as a barcode as well, just by, we're going to separate out each, so that 2 we're just going to view as 2 different bars. And so we have 2 bars that go from 2 to 4, and then we have 1 bar that goes from 1 to 5. So yeah, barcodes are really just the same thing as persistence diagrams. It's just a different way of visualizing the data, but it's the exact same data.